So it's my pleasure that Peter Morgan agreed to join us today in giving a presentation about his work. He is from Yale University, and I would maybe like to say a few words how this came all to be, that he's now giving the presentation. And it started at the Q-Turn conference, an awesome event, which I hope you will all join for the next edition. And I somehow stumbled across Peter's poster there in the online poster session, but it was just about to close. And anyway, we were chatting a bit in the social event there, and I thought, okay, hey, what he's doing sounds really interesting. So I'm very happy that he agreed to give a talk at IQOQI. And yeah, Peter will give us a talk about how you can deal with the measurement problem in a signal analysis way. And I think he can also show us how you can actually combine classical and quantum mechanics in a nice way if you start thinking or putting it in a different picture. So I'm very happy that Peter is giving the talk today. And yeah, Peter, the stage is yours. I want to tell you, everyone, we will record the presentation. So if you are uncomfortable with this, yeah, just that you know.
Talk.
Yeah. Okay. Thanks a lot, and Peter, the stage is yours.
Thank you, Martin, and thank you for the invitation. I'm really looking forward to showing you a little bit about this. So I'm very much going to try to weave signal analysis through everything I'm going to say. There's going to be a first section in which I, a theorist, will talk about experiment and will make no sense whatsoever, but you will make what sense you can of it. And then I'll head off into algebraic territory. And in the middle section, I'll talk about the collapse of the quantum state as a joint measurement construction. And then finally, I may or may not have time to go into how we can approach quantum optics and other quantum field theories in a slightly classical way that I think can let us do interacting quantum fields in a more natural way than we might be used to from quantum field theory textbooks. So if I'm going to talk about measurement, then I have to say that I'm against measurement of particle or system properties. On the other hand, I'm in favor of actually recorded measurement results. So what you must have for a journal editor is slightly less of a shifty split than is the Heisenberg cut, I'd say. And a journal editor may be capricious about your data, but a theorist with a room full of Wigner and his friends is a lot more dangerous. You really want to stay away from them. So that's to say, I'm going to say no. You shouldn't be talking about the spin of the electron was up or down. But on the other hand, I'd say yes, we should be talking about the average signal level on some signal line somewhere was about such and such a level at such and such a time. Excuse me, that is my finger trouble. Yes, excuse me, right. My finger is more nervous than it usually is, I think. So signal levels are correlated with the surrounding noisy field, whatever that is. And I hope by the end of this talk, you'll have some sense of how I'm thinking about that noisy field. We want to analyze details of the signals in useful and interesting ways. We want probability models for the statistics of all the data sets that we've collected, the gigabytes and terabytes of data we have, of actually recorded measurement results with all the noise that has. We'd also like there to be useful engineering tools and guides for the intuition, because we want ideas for what calculations and experiments to do next. Just having models really doesn't help you very much. You need details. So my claim is that quantum mechanics and quantum field theory are signal analysis formalisms. They're about the signals out of devices. It may at one point have been the case that there were needles going left and right and people were writing down, oh, 3.6 volts. Nowadays, we're making that kind of record at megahertz and gigahertz rates. And they're giving us a signal, which is effectively a field theory in 1+0 dimensions already. We really should be thinking about what we're doing in a field theoretic way, just from the point of view of signals. classical signal analysis is about Fourier and time frequency analysis. And so Wigner functions are entirely natural in classical signal analysis. And as well, the Fourier transform also appears when we discuss the relationship between probabilities and characteristic functions, which are just the Fourier transform of probabilities, and back again. And hence it's all about L2 Hilbert spaces. And I'm going to discuss later, as Martin said, Koopman's introduction in 1931 of a Hilbert space formalism for classical mechanics, which makes it possible to discuss classical and quantum mechanics in more or less comparable ways. So we do see events on signal lines. I'm going to discuss that in a moment. But I suggest we should back away from talking about particles until we're certain that introducing the idea of a particle for a description of a particular experiment is actually not going to lead to any logical problems. And of course, that's a tall order whenever we're talking about quantum mechanics. But yes, of course, there are tables and chairs and experimental apparatuses. It doesn't give us much problem to introduce that as an idea. So I think a focus on signals connects with Bohr's insistence on classical description. So of many, many places where Bohr writes many, many things, I picked this particular one. It's decisive to recognize that. However far the phenomena transcend the scope of classical physical explanation, the account of all evidence must be expressed in classical terms. So I think there is a way, however, to reconcile Bohr and Einstein by extending Bohr's doctrine of classical concepts. We can make non-commutativity, contextuality, incompatibility, and all that a natural part of in classical terms. What I'm going to call CM+, and indeed that's what I call it in a paper I was published in Annals of Physics last year, by adding hidden observables from signal analysis into classical mechanics. And of course, this is the opposite, so to speak, of what we usually do, which is we try to add hidden variables into quantum mechanics to make it look more like classical mechanics. Let's do the opposite. So here is Frank. This is going to be a little whimsical, but hey. So Frank is an APD. The engineer worked hard to create him. Frank is made from exotic materials. He's using exotic processes, and it's taken us centuries to get to the place where we are now. And every decade we have new, fancier materials and more exotic things. Frank is definitely not conscious, but he certainly is much more complicated than just the rock. So Frank tells anyone who will listen to his signal line here how he feels, and he'll tell them at megahertz and gigahertz rates. Frank mostly burbles along while he watches and feels his surroundings, but occasionally the burbling turns into bang, an event. And that's the thing we record, that at that time an event happened. Of course, that's more interesting than using devices that don't do anything. But Frank, it's not clear to me that Frank knows anything about particles, but he's just getting cross at his surroundings. And of course, as soon as Frank gets cross, Frank has electronics all around him, surrounding him, and tells him to calm down, come on, burble again, then we can get cross again in the future. So Frank sometimes gets cross, even when it's dark and quiet. And of course, that's the notorious dark rate. We try to keep that as low as possible, but still it's always there. But Frank gets cross differently if his surroundings are different. So if we introduce a laser on the other side of the moon and point it, well, sorry, on the near side of the moon, and point it at Frank, then the statistics of events will change ever so slightly. And precisely how those statistics change will tell us in detail exactly what kind of laser it is and where it is. And if we collect data for long enough, we'll be able to tell an awful lot about the laser on the near side of the moon. So Frank does tell a story, even when he's not cross. If we look at this signal here will not be the same if we're pointing a laser at Frank. It will be different in subtle ways that will require us to do some real big data analysis to figure it out. But that's precisely what Zlatko Minev did when he listened to his devices. And he said, by listening to this, I can actually devise a support system that stops Frank from even getting cross. Now, I think it's worth talking about Frank's frequency scales here. The optical scale is approximately the petahertz scale. And that's 10 to 9 times faster than the thermodynamic scale of events, where it's more or less megahertz rates, plus or minus 10 or 100 in scale. And then, of course, there's the electronic scale at gigahertz down as far as terahertz, depending on exactly how your electronics are. So this is the beating heart of the apparatus. It's every picosecond, And this is equivalent, if you take that to be a heart rate of 1 hertz, that's equivalent to measuring every 30 years, saying, oh, an event, and trying to determine stuff about the heart from the information you have about the thermodynamics over that huge scale difference. So I'm going to discuss Gregor Wies's experiment, which you guys will be more familiar with than I am. He gives Alice and Bob two APDs each, an electro-optic modulator, and he gives them a clock. And then Alice and Bob both save only the times at which events happen, which APD it was, and what the EOM setting, the electro-optic modulator setting, was at the time that came out of the random bit generator. So this compressed record ignores and doesn't analyze anything of the rest of the APD stories. This is very, very compressed data. So this is Gregor's experimental results. Every one of Alice's events that were seen in the 10-second period that also had, within 100 nanoseconds of it, a measurement was seen by, event was seen by Bob. So there's 20,000 events out of a total of 400,000 here. And the 16 different colors represent the different the different values of the 4 APD and the electro-optic modulator bits. The 4 shapes tell you which of the, the 2 bits for Bob were, and the brightness tells you what the 2 bits for Alice were, and then the diagonal tells you which, the color tells you what it is on, which diagonal it's on. So if we zoom into the 3 nanosecond scale, we see that there's a large number of coincident events, and most of them are green and yellow. And if we now, having identified those events, we forget all the absolute timing information, then we obtain these 16 histograms, and then we discard the relative timing information, and now we have 16 plain numbers. We put those plain numbers into the standard calculation, the one you can find in Gregor's thesis, and that gives us a violation of the Bell inequalities. Now, these 16 histograms come from results which come from when the electro-optic modulators have different settings. So the raw data subensembles are not jointly measured in the same context. And I'll here, because it'll be important in a couple of slides' time, that once equilibrium is reached, the Bell inequality violation can be broadly independent of the distance from Alice to Bob. It doesn't matter whether it's 1 meter or 100 kilometers between them, but it does matter about how fast the equilibrium will be reached. So in quantum mechanics, we model Bell violating statistics using non-commuting operators, whereas in classical mechanics, as usual, we don't have non-commuting operators available to us. But classical probability theory is well aware that there are families of events that are not commensurable. So their frequencies must be measured in more than one sample. And that's precisely the situation we have when we were considering the electro-optic modulator, because they can't have different settings at the same time. So the raw data subensembles are incompatible. And this is more the modern word for the situation that is described by Petovsky. So as a signal analysis uses signal functions, and effectively that is to use non-commutativity routinely. It's also the case that the identification of events on a signal line is non-Markovian. It requires memory, because we can't just look at the signal level here and say, oh, an event. We have to know that an event happened recently and not report the event twice or 100,000 times. So at the same time, the signal levels at different times are compatible. We can measure the signal here, 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 and here, and compute joint probabilities for the measurements we make at those times. And a little later, I'm going to discuss Koopman's Hilbert space formulas of the classical mechanics, in which we can use non-commutativity as needed whenever we want to model these contexts, as I say, CM+. So taking classical mechanics to be unable to use non-commutativity sets up a straw man argument. If you tie the arms of classical mechanics behind its back, then quantum mechanics can win every time. So just before I enter into an algebraic approach, real algebra land, just to suggest that there is a way of modifying Gregor's experiment that I think is quite motivated by a signal analysis way of thinking. So at a fine-grained scale, Gregor's experiment is not at equilibrium, because of course there are events happening very irregularly. It's really not time translation invariant. Whereas at a coarse grain scale, Gregor's experiment is at equilibrium. Over any 1 10-second period, we expect that we would measure the same violation of the Bell inequality from one time period to another. So that is time translation invariant. And indeed, the violation of the Bell inequality is effectively a thermodynamic property of the experiment. So what happens, however, when we first turn on the power? The event rate will increase in each of the 4 APDs, of course. The coincident event rate will increase. The violation of the Bell inequalities will increase at some rate. But are these rates the same? How are they different? And how do these rates change at different distances? As far as I'm aware, we really don't know the answers to these questions. These rates are technologically important as well as foundationally significant because sometimes we have to turn on the power. And when we do turn on the power, we want to know how long it takes for Alice and Bob to have available to them the violation of Bell inequalities that we're going to use as a resource. So turning on the power is different from using a pulse laser in a sense. APD events don't give us a tomographic analysis of the complete electromagnetic field state. Just seeing 0 events on 4 APDs don't prove that it's the vacuum everywhere in the whole of the rest of the apparatus. So I think what we have to do is use modulations of the optical frequency carrier at, say, between the 1 Hertz scale, which would be more or less turning on the power, and the gigahertz scale. And so this is a very much response to a modulation sort of approach to the Bell inequality violation. So it's non-equilibrium. So now diving into the algebra. Think about it, these things in terms of signal analysis. Just say, well, there are measurements, M1, M2, M3, and if we have 1,000 or 1,000,000 of those things, then we have a signal. And each of these linear operators corresponds to a random variable. And the spectrum of each linear operator corresponds to the sample space of that random variable. And then we have a non-commutativity and associativity to taste. Now, to make contact with the experiment, we want to introduce a statistical state that tells us for any given measurement what we expect the average value to be and what we expect the moments of that distribution to be. So it gives us a whole probability distribution by doing that. In algebraic quantum mechanics, there's basically has emerged a set of 4 constraints that need to be satisfied for us to be essentially in the Hilbert space regime. So it has to be positive, which is just to say the variance of the probability distributions will be positive. It should be compatible with the Hermitian conjugate. We have von Neumann linearity, so that whether A and B commute or not, we still have linearity, and normalization, just the sum of the probabilities, should add up to 1. So we can also use measurement operators to modulate the state to give us different expected measurement results. So we can construct rho A by bracketing the measurement operator M with A and A dagger. And this also satisfies the axioms for a state. And this allows us to construct a Hilbert space using what's called the Gelfand-Naimark-Siegel construction. So what we've done here is we've started from measurements and states and come to a Hilbert space instead of the usual approach for quantum mechanics, of course, which is we start with a Hilbert space, we introduce tensor products as well, and then we discuss what we can do with the operators that gives us. But in an algebraic approach, there's no tensor product. And there are no systems. There are just different modulations we can apply to the first state we thought of, and that gives us different signal measurement results. So this actually makes many no-go theorems of the last few decades just not apply to an algebraic approach, because the tensor product is fundamental to many of those no-go theorems. So now to apply what I've just said to you as an approach to quantum mechanics and classical mechanics. Classical mechanics is an algebra of functions on phase space. That's absolutely the standard story. But it has 3 binary operations: addition, multiplication, and the Poisson bracket. And this tends to be sort of, I mean, everybody knows it's there, but we also ignore it. The Poisson bracket acts on the Hamiltonian function, for example, to give us a generator of time evolution, which I'm going to call ZH, which just applies the Hamiltonian using the Poisson bracket to any function u. And that's called the Liouvillean operator in the literature. And we can use the Poisson bracket on other functions to give other transformations ZV. Now, it's the case that these functions ZV do not commute with the usual just multiply by W, which I'm going to denote by YW. YW just means multiply by W. So we have, in classical mechanics, this as a non-commutative algebra of operators with just two operations, now addition and composition. Now there is a huge difference, except it's tiny compared to the in a sense, because we have now got non-commutativity naturally in classical mechanics. But the Hamiltonian operator in quantum mechanics is bounded below, but the Liouvillean ZH is not. Now, this positivity of the Hamiltonian operator results in all sorts of analytic properties for quantum mechanics. And so there's a sense in which we can think of quantum mechanics as just, but certainly as an analytic form of classical mechanics. They're both about measurements of, and so on. So we can use the Y's and the Z's of a more powerful CM plus without restriction. If we do, then there are many more places in which we don't have to use quantization of the correspondence principle. It's very much a choice, however. We want to use the beautifully analytic properties of the Hamiltonian that are given to us by the positivity of the Hamiltonian, but sometimes we'll want to do the opposite way. So to apply this to the simple harmonic oscillator, the Poisson bracket is the trivial example here, and that allows us to construct for the momentum function using the Poisson bracket. We just get derivative with respect to Q, because that does not commute with multiplication by Q. So we get this, and we get the same sort of thing for the multiplication by P and ZQ. So this is the Heisenberg algebra. And we can do the same construction for the Hamiltonian function, which is just multiplication by half Q squared plus P squared. And for the Liouvillean operator, we obtain this differential operator, which, as I said in the previous slide, is not a positive operator. And now we want to introduce a state. And the natural thing from a classical point of view is to introduce the thermal state, and in particular the Gibbs state, because that just makes very few assumptions in a way. And that just gives us a Gaussian expression that generates all the moments of probability distributions that you might want for YQ and YP. And we can do the same for ZP and ZQ. And indeed, because this is a representation, this is the Heisenberg algebra, we can construct the YQ and ZP in terms of raising and lowering operators, essentially just as we do in quantum mechanics. And in this classical simple harmonic oscillator, as for quantum mechanics, we can construct new modulated states, and hence we can construct a Hilbert space of states. So instead of trying to map Q and P to the quantum Q and P, which quantization tries and fails to do because they're different algebras, we try, and we can, map CM plus to quantum mechanics, Q and J partially Q to Q1 and P1, and similarly for this, except crucially, KT is not Planck's constant. And I think for this, to understand this, we have to go to quantum field theory, which is why that's what I'm going to talk about later. So before I discuss the collapse of the wave function, which is the next slide, I feel I have to talk about interpretation probability for just a moment. So we can use any interpretation probability. If one of these is the one you like, just do it. Of course, there just has to be, because we're experimentalists too, physicists at least, there must be a connection to experimental raw data, to its statistics, and to how we choose the subensembles of the data. So as a second point, in the past, there's a finite quantity of discrete experimental raw data, so we could perfectly well use a finite dimensional Hilbert space to describe all that. But what we might do in the future is a continuum. Statistics about the past anticipate a continuum of probabilities about the future. And exactly how we want to interpolate and so on is a deep matter that requires us to enter into much higher order mathematics than just discrete, just finite dimensional Hilbert spaces. And again, I think this pushes us into using field theory. And finally, I introduced the Gibbs state without really any justification. I think we should accept, just as quantum theory does, that a thermal state either just is. It just is, there's that probability distribution. It works, just use it. It's just, or it may be that it's continually being kicked by a heat bath. And indeed, it's essentially, there could be, at every possible scale, noise that's caused by Brownian motion. But perhaps there is a scale at which, well, it's just noise and that's it. There's nothing more to say about it. we'll always be looking to see whether it actually might be caused by a Brownian motion that's bubbling up from below, but still. Okay, so collapse of the state. This is the mathematical heart of this paper. This is in a recent, still an archive paper. If we have a measurement A that has a discrete spectrum alpha I that's associated with projection operators PA, that of course are orthogonal, then we can construct what I'm going to call a probability density generating operator. And I'm going to say that a lot, which then a state rho gives us a probability density, which is just a projection to the values alpha I, and with these probabilities associated with each of those being the state applied to the A projections here. So if we have two such measurement operators that commute, we can construct a joint probability density trivially, just using the usual product. We can take a product of probability density generating operators for A and for B, and we can expand this out and get out a delta function that isolates to the joint spectrum for alpha I and beta j. And this is a positive operator, pi pb, because it is because A and B commute, and we apply the state, and that gives us a probability for that joint spectrum. But if A and B don't commute, we can't construct a joint probability density this way. But a remarkable feature of the collapse of the state, and I don't know that this is in many places in the literature, and I think it should be everywhere, it lets us construct joint probabilities using non-commuting operators. So if we measure A and we get the alpha I result, then we say that the state collapses to this new state, rho I, which we can construct just by taking the A projection operators and bracketing the measurement that we want to make next. And then we measure B. So we obtain a joint probability density, rho for A followed by collapse followed by B, which is just the probability of getting the alpha I result, followed by the probability density for measuring B in that state we've just got by projecting to the measurement by the measured state collapse. And if we multiply that out, we get a joint spectrum for the alpha I and beta j, together with this positive operator, the B projections bracketed by the A projections. And because that's a problem, then it's positive, and it's not only positive, it's also normalized. And so the state, this gives us a joint probability density. Now we could equally well have constructed any joint probability density actually, using a different state and a different operator B prime. We just choose B prime and rho prime in such a way that for starters, B prime would have the same spectrum as B, so it has beta j as the spectrum, so we get this projection to the values alpha I beta j. And now A and B prime commute, so we can construct a joint probability like that, and we can make sure it's the same as this. So we can think of collapse not only as a dynamical process, we can think of it like that, it's in the math, we can think of it that way. But we can also think of it as just a joint probability algorithm. The joint probability for observing A followed by collapse followed by B is just this expression, which is just the state applied to this joint probability density generating operator, which is equivalent to just an ordinary use of, because these operators commute, what they're called in the quantum mechanics literature, they're called quantum non-demolition measurements. And Belavkin already in 1994 essentially has all the math that I'm doing here, and it's been more or less ignored since then. It's hard to read paper, to be frank. And then Tsang and Caves in 2012 in an article in PRX calls this effectively the same construction, what they call quantum mechanics free subsystems. I recommend that paper to you. So we can make collapse act on other measurements instead of on the state. That's essentially how I constructed the mathematics in the previous slide, which may have looked a little unfamiliar, but hopefully nonetheless didn't go fly by too fast. So we can define what I call a collapse product of two probability density generating operators with this to symbolize it, A followed by collapse followed by B, which is just take the projection operators and bracket PB by the A projection operators. And that gives us the expression we had on the previous slide. So I'm going to introduce a notation for the these generating operators because I'm going to use a lot of them now. A with a bullet above it. So To generalize to more than two operators, I think the best thing to do is to use what's called the sequential product. And this has been in the literature since about the 1990s, which takes two positive operators, x and y, and constructs another positive operator, because we can take the square root of a positive operator, and so we do that. And if x and y commute, this is just the same as multiplying x by y. But if they don't commute, this nonetheless gives us a positive operator. So we can use it to construct a joint probability density generating operator, excuse me, using this construction, because this is a positive operator and it's normalized in the right way too. So to look at that in a little bit of detail, which is pretty sad, but still. So we're going to bracket the B projection operators with the A projection operators. And then we're going to bracket the C projection operators by the square roots of that. So that's this expression becomes this horrible thing here. So this sequential product is non-commutative, it's non-associative, it's nonlinear, it's left operand. Really, there's nothing you'd less like to work with. But this means we kind of have to. Anything we're going to do that produces positive operators is going to be complicated. But this is different if we do it the opposite way around. If we bracket the C projections by the B projections and then bracket that by the A projections, we get a much simpler expression. But this means that any different bracketing, and there are lots of them, is going to give us different measurements. Different joint probability densities are going to come out of each one of those. So now we're going to look at what this looks like for signal analysis. If we record a signal level at nanosecond intervals co-measurably, so they are compatible measurements, we can model the statistics of those measurement results equivalently using a sequence of non-commutative operators with collapse in between every single one of them, every nanosecond, excuse me. Or we can use a different state and a sequence of commutative operators that are quantum non-demolition measurements with no collapses ever. These are empirically equivalent, so we can use whichever is more useful. But they're different if we're realist about our models. And of course, people in the last couple of decades have become really, to my mind, ridiculously overcommitted to particular quantum states. And of course, there are practical differences to using the one or the other, which I won't go into, but I think they're a little scary. So this, I think, can be viewed as different collapse conventions. And indeed, we can talk about that differently as collapse pictures, similarly to the way we talk quite happily about the difference between Schrödinger and Heisenberg pictures, even though they are really significantly different in many ways. Certainly, if we're realist about those, it gives a very different view of the world. So we can have many collapses in which they're effectively a collapse after every single measurement, or we can bracket in a different way, essentially tail-ending everything, so there's effectively just one collapse before the last measurement. Not quite exactly what's there, but you'll have to look at the math to figure it out. Or we can just use commuting operators, quantum non-demolition measurements, no collapse. It's relatively straightforward. Okay, so the sequential product requires a logical ordering, but we can do either ordering. We can take the B projection operators and bracket it with the A projection operators, but we can do the opposite. And really, time ordering doesn't have anything to do with this necessarily. Both of these constructions give us a joint probability density. And so we can use whichever seems most useful, using different states depending on what you have to do. Time reversal is made much more complicated by this construction. I mean, whenever people discuss collapse and time reversal, it inevitably introduces complications. Really, if you're going to talk about time reversal, you want to really talk in terms of the quantum non-demolition approach, to be honest. It's going to simplify your discussion endlessly. Now, the mathematics of decoherence, of measurement as interaction, and even the mathematics of the observer, all that is, of course, mathematics that is not going to go away. It's still perfectly usable. We're going to use it just as we ever have. But we don't have to use those discussions. Collapse can be just about joint probabilities and about how those relate to the statistical experimental raw data. That, in a way, is all we care about. But we don't have to give up metaphysics in doing this, because we're always looking to the future, to things which we don't yet have experimental evidence for. And that's what metaphysics is. It's anything that we don't have experimental evidence for. So finally, for collapse of the state, I'll talk about repeated measurements, which is obviously one example of a joint measurement. So suppose we do two measurements, the same measurement once and then do it again. So we can model that by using the same probability density generating operator done twice with different values u and v. Next gives us a joint probability distribution. And that, however, we can simplify to just as a delta function for when u equals v. It's only non-zero when u equals v. So perfectly repeated measurements, so long as the evolution is unitary and so long as there's no collapses. There's quite a few constraints in here, but nonetheless, and it's not very rigorous, of course, because I've used delta functions in a kind of ad hoc kind of way here. But still, there's perfect correlations. So this is quite similar to Mott's result for a track in a Wilson cloud chamber, in that Mott constructs a mathematics in which the quantum state does not determine where the first event of a track happens, but once that first event has happened, then where the track goes afterwards is determined by the whole experimental apparatus and by that first event. So outcomes are not determined, but correlations are perfectly determined so long as there's no collapse. Okay, so loosely we can say that quantum mechanics, just as Koopman classical mechanics is, conditionally supercorrelated. And of course, this is a riff on superdeterminism, which I do not agree with essentially. Now, a throwaway line here, which I'm not going to talk about, but in quantum mechanics, as in classical mechanics, the mathematics doesn't have any branching in this way of doing it, at least. There's just perfect correlations, and that doesn't really allow for branching. Okay, so now I'm going to step into quantum random fields, but do it in a signal analysis way. I think this makes it more natural, makes it easier. There's really no need to look at the quantum field theory textbooks to understand this kind of way of thinking. The abstract measurements are phi f1, phi f2, phi f3. So instead of labeling these m1, m2, m3, m4, etc., we label them f1, f2, f3. And each one of these test functions might be one at this value or this value. Each one says different things about the way in which you're particularly looking at the signal in this area, in this region. So modulation functions in quantum field theory and algebraic quantum field theory are known as test functions, but they're known in signal analysis as window functions, precisely because it shows us a different way of looking at the signal. So we can think of these modulation functions as smooth and having smooth Fourier transform. They can be almost, but they can't quite be pure point or pure frequency measurements. You can have something like these, but you can't have something that is a delta function because that gives us mathematics, which is unpleasant. So test functions in code, things like sample widths, pulse widths, and higher order details as you get in here. Now, there are no smallest measurements because this we can split into two parts in many, many different ways, but there are always smaller measurements, those precisely splitting those into two parts. And there are always measurements between other measurements because we always add different modulation functions together to give us more different measurements, and we will be using those. So mathematically, just to say, we work with the dual space of the operator value distributions. And I'm going to call phi f an f modulated operator. We're just not going to talk about the phi of x, which is the meat and drink of quantum field textbooks. So I suggest that what we're doing here is we're actually discussing the field as a field of measurements. I find it much more useful to think of fields in this way. It's a field of measurements, and indeed it's a field of algorithms. It's not a field that we measure. The field tells us what measurements we perform. That's what the test functions tell us, not what the measurements are of. The test function has nothing to do with what the measurements are of. It just tells us how we're looking at the world. So instead of modulating classical fields, we're going to modulate expected measurement results, and we're going to modulate probability densities differently from place to place. So having discussed measurement operators on the previous slide, I'm going to talk about states. So a vacuum state is a Poincare invariant state. So in this particular case, we want to know what the expected value will be for any operator which we construct as the product of F modulated electromagnetic field of the electromagnetic field, however we construct it. And for a Gaussian state, we have a generating function, which is just a Gaussian characteristic function, more or less. And now don't be scared, but now for multiple operators, we can just take multiple versions of this generating operator, one after another. And this gives us this expression. The reason I'm showing you this, because you're not going to get this in one session, I should think, is that this has a Gaussian noise term. That's all this is. And this expresses the incompatibility of the Gaussian quantum field. This single expression represents the whole of the algebraic structure. The same is true for the simple harmonic oscillator, same is true for the Klein-Gordon field, for the quantum optics. It's just that we use a different pre-inner product for each of these, gives us different geometrical content, but exactly the same algebraic content. This is everything about the algebraic structure. So for the Klein-Gordon field, we use the wave number components of the test functions to construct this inner product, and then we project to just the forward-like cone. For quantum optics, there's a more complicated expression because we have a bivector valued test functions, and this object is in fact a space-like 4-vector. And so this inner product is in fact negative definite, and that's why we have a negative value here. So this is positive, and now we're projecting to the forward-like cone instead of the forward mass shell. Both these constructions are manifestly Lorentz invariant. So I feel I have to discuss, because really it's essential to understand the distinction between quantum fluctuations and thermal fluctuations in this perspective. For the Klein-Gordon field, the quantum field vacuum is Lorentz invariant and is just a projection to the forward mass shell. For the thermal state, it's exactly the same projection to the forward mass shell, but it also includes a weight which is proportional to the frequency of the particular test function component. And this expression here interpolates between the ordinary Klein-Gordon quantum field vacuum and what is entirely the normal thermal state if you were doing classical field theory. This is the thermal state for that theory. Now, there's a significant difference which refers back to what I was saying earlier, that the classical thermal state doesn't restrict to positive frequency. There is no theta k0 in here. So the classical thermal state does not have the nice analytic properties of quantum field theory. So we're going to want to continue to use quantum field theory whenever we want those nice analytic properties. So the distinction between quantum and thermal noise requires the Lorentz symmetry. And that means we have to be working in at least 1 + 1 dimensions, because Lorentz symmetry requires you to be working in 1 + 1 dimensions or higher for there to be such a concept. And that's why we have to work with field theories. So the vacuum state is Lorentz invariant, thermal states are not. Quantum fluctuations are Lorentz invariant, thermal fluctuations are not. When we use quantum fluctuations as a resource, we might perhaps actually be able to do quantum computation using thermal fluctuations if we can control temperature really, really accurately to be 100 Kelvin exactly, 100.00000, as good as we don't actually have to control Planck's constant because it's always constant. Then we could do quantum computing using thermal fluctuations instead, perhaps. Speculative idea. So here's an example of how modulation changes probabilities. So for a Gaussian state, if we have an F-modulated electromagnetic field and we use this characteristic function generating operator, then we obtain a characteristic function which is just a Gaussian, and that gives us a probability density in the vacuum state, which is, again, just a Gaussian. So if for a coherent state, what we do is we take a G-modulated electromagnetic field, we construct for ourselves a unitary operator, and we bracket the generating operator we used before with the unitary transformation. Then we obtain a displaced probability density. So that's what the G-modulated electromagnetic field does as a symmetry generator. It generates translations of the normal distribution that is the vacuum state and constructs this instead. And the amount it translates, it depends on the commutator between the F and G modulated electromagnetic field. So if F and G happen to be very close to each other, then there will be quite a large coherent displacement. But if F and G are far apart, then there will be almost no displacement. So we effectively displace the field by different amounts in different parts of space-time. So now we also have, for what I'm going to call a once-raised modulation using the G-modulated electromagnetic field, this is something you would call a one-photon state, where we use the operator FG bracketed around the generating operator to give us this characteristic function. And when we take the Fourier transform, the Fourier inverse transform of that, we obtain the probability distribution. So when, this is what I'm going to call the resonance overlap, which you can look at later if you want, that can be either small if F and G are very far separated, in which case you just have the vacuum state where there is a large separation. But where F and G are close together or overlap a lot, then the probability distribution you'd expect is this 2 maxima result. So this is what a one-photon state is from this approach, this signal analysis approach to quantum field theory. Obviously, this is just a completely different way of thinking about quantum field theory than working with quantum optics in the ways that you're probably used to. We use the vacuum state as a broadband, noisy carrier signal for probabilistic modulations. Instead of just using a 10 gigahertz pure wave number as a carrier signal for our modulations, we're instead using all possible wave numbers that lie on the forward mass shell or on the null light cone, and that's what the vacuum gives you. It gives you a carrier signal, which you then modulate. So that's the way of thinking about these things in signal analysis terms. So I'm not going to make as much as I thought I was going to make, but still. So I want to really bring together random fields and quantum fields. An alternative way to construct the same Gaussian state is in some ways more familiar to you, I suppose. And that is to construct the F-modulated electromagnetic field as a sum of raising and lowering operators. And those raising and lowering operators satisfy the Heisenberg algebra. And that gives us a non-trivial commutator between the G-modulated and F-modulated fields. Now, for the complex Klein-Gordon field and for quantum optics, we can find an involution for which this expression is satisfied. And this is playing fast and loose with the inner product, with the complex conjugate, and with this new involution. And this gives us an object, which I'm going to term chi-f, which we're going to construct using exactly the same operators as we had before, using the raising and lowering operators. And for this object, it is everywhere in space-time, it commutes with itself. So this is what I'm going to call a random field. Indeed, this is more or less reasonable, which is, in quantum mechanics terms, is a commutative subalgebra of quantum non-demolition measurements that generates the whole of the Hilbert space that we would usually generate using the F-modulated electromagnetic field. Now, clearly, the algebra generated by the chi-f's is not isomorphic to the algebra that's generated by the F-modulated electromagnetic field. And we have to be clear, this involution is Lorentz invariant, but it's not translation invariant, and it's not local. So this is really sweeping a whole pile of can of worms under the carpet to just introduce this. So this is, however, not the Broglie-Bohm, because this is naturally Lorentz invariant. And for quantum optics, just to very quickly show you approximately what's happening here, we take the two polarization components of the test function f, and one of those components, we reverse it in the way that this suggests. So this is really messing with locality. And I won't try to explain to you in any detail what that really results in. So before I talk about quantum field theory, which I'm not going to have time for, about really deforming quantum field theory in a good way, I do feel I have to talk about what is really an elephant in the room, I think. And that is quantum optics and almost all quantum mechanics uses state transition probabilities as if they're local. And of course, they're really not. If we take this the way we usually write it, it's actually just this, and that's the trace of this product of operators. So that's a measurement beta beta in a state rho alpha that we can write like this. So the measurement beta beta is non-local in the sense that it does not commute with the F-modulated electromagnetic field for any test function you can choose. And a state is also non-local insofar as it determines expected measurement results everywhere. So rho alpha will tell you the result of a measurement B, no matter where B is in space and time. So now there's a construction we can introduce for a state rho, which basically follows what we do usually use when we use a state transition probability, and that's to construct a vacuum projection operator by this algebraic construction, so that V squared is equal to V. And if we do that for the state rho alpha, we just obtain V alpha is just this projection operator. And if we allow the use of this construction, the algebra generated by the vacuum projection operator and the F-modulated electromagnetic field is isomorphic to the algebra generated by the same vacuum projection operator and the F-modulated quantum non-demolition operators that we've been using. So anything we can model with quantum optics and the vacuum projection operator, we can also model with this version of classical optics and the vacuum projection operator. But note that there's a Lorentz invariant noise in here. This is very much not your great-grandparents' classical electromagnetism because of that Lorentz invariant noise. Okay, I was going to talk about the Whiteman axioms and about how there are many ways in which they really seem much too strong if you think in classical terms about them. And there are ways of deforming remember this equation that I suggested gives you the whole structure of electromagnetism. Instead of trying to deform the Lagrangian, we deform this instead. And there are many ways to do that once you start thinking in these terms. No, I won't talk about this or this or this or this or this or this or this, and we get to the last slide, number 30. So one-dimensional signals, we can embed them in a quantum non-demolition system of measurements in 1 + 3 dimensions. Everything becomes, in a sense, a classical field theory with noise. What quantum field theory does is it converts that construction into an analytic system in which the Hamiltonian is a positive operator. Instead of, in the classical system, we have the Liouvillean is not a positive operator, which messes with our heads in a really unfortunate way, to be honest. So if we think in terms of fields and signals and events, I find, the boundary between quantum and classical is still subtle, there's no question, but it's much less mysterious than if we think in terms of particles and system properties, which just get our heads in a much bigger mess. Both quantum and classical theory are frameworks for sequences of measurements and hence for signal analysis. And indeed, their framework, quantum theory in particular, is a framework for sequences of measurements precisely because the collapse of the state allows us to construct joint probabilities and allows us to work as if we were working with quantum non-demolition measurements. But we still need non-commutativity to model non-contextuality as we obtain when we see a violation of the Bell inequalities. So Lagrangian deformations are not the only way to construct interacting quantum fields, and I'll finish with my reading of the literature in physics, and particularly in quantum mechanics, obviously, is that quantum and classical have been converging in many ways for decades. Generalized probability theories have been there for 40 years at least. Phase-space methods, Wigner functions have been used for much longer than that. Contextuality has been discussed for the last 20 or 30 years, really quite vigorously. Non-demolition measurement has been in the literature for 30, 40 years. Kuhlmann classical mechanics has been there since 1931, but has just been forgotten and really should not have been forgotten. Time frequency analysis, been the signal analysis literature, and the use of Wigner functions in that literature has been there since at least the 60s. Stochastic methods, you can find stochastic electrodynamics is in the literature since the 60s and has had virtually no effect on the quantum field theory literature. It just does not make a connection. If you actually look at it through the mathematics I've been looking at quantum mechanics through, it actually does make sense. And it's a little bit of a shame that it didn't make sense in the 60s, but it didn't, and rightly so, to be honest. But there are modern stochastic methods that are being introduced now in the literature, which really expand on the work that Nelson did in the 60s for quantum mechanics. And finally, there are semi-classical methods, which is a whole mess, where people are really introducing many pragmatic bits of mathematics in very ad hoc ways, and it all needs to be tidied up something terrible, which I think, by looking at quantum classical in a very similar sort of way, both in a Hilbert space formalism, we can really do some tidying up about that. I'm not going to mention this because it just will introduce a can of worms. And these are 4 papers that more or less include the mathematics at least, but not with the whole focus on signal analysis that are given here. Thank you very much for your attention.
Thank you very much, Peter.
Thank you.
Was great. I think we are few people enough that it's possible that just people unmute to ask their questions.
Sure.
Without me moderating it, I think this should work the best way. So
sure, and
yeah.
I can open up the chat as well, can I? And I can open up, I've opened up a chat now, which I hadn't opened up before, if anyone wants to ask a question that way. But maybe I know there's a lot, but still.
Maybe I could start with one question of you mentioned this striking difference in the end between classical and quantum mechanics, that the Liouvillean is not bounded in classical mechanics. Do you have like any interpretation of this, or does this tell us something about incompleteness of classical mechanics in some way, or?
I don't think it does. I mean, in many ways, we just work with a Hilbert space and all the operators that gives us. And then we pick particular operators as particularly significant. So the Hamiltonian is significant because it generates time-like evolution in the quantum mechanical way. So if the time-like evolution is generated by a different operator that's not positive, then all sorts of things get changed. And I think this is at the root of the problems that have been faced by geometric quantization, where the final step, because most of what I've said here is actually, you can find it in the geometric quantization literature. It's just that there's a final step that just doesn't go through smoothly when you try to do this as a quantization. And I'm not trying to do a quantization. That's precisely why I say, let's not make the step from KT to Planck's constant. Let's stick with using one or the other. But because if you use a classical structure, then you're closest to general relativity. And yet, if you have all of the algebraic structure of quantum mechanics, you've got some possibility, you've got more possibility, it seems to be, of doing something with quantum gravity. I mean, this says, let's make classical mechanics more sophisticated so that it can talk just as well as quantum mechanics does. And then we can talk between CM plus and general relativity. And now we want to do the same kind of thing to general relativity. Of course, that's something for the future. I don't know enough about general relativity, and I certainly don't know enough about the literature of quantum gravity to speak to this at all, except that this is obviously something that people say. How do we get quantum mechanics to talk to general relativity? Well, this gives you a way of sorts. And as I say, it's been in the literature in one sort of way or another. I'm frankly expecting that this will be also just the same as Bilavkin's. I mean, he produced this stuff, which is exactly what I'm doing, and didn't make the connection in a way that let people actually use it. And that may be the fate of what I'm doing too. And I'm quite sure that some of the things I'm doing, people will say that's nonsense. Just if one or two of the things I'm doing possibly might ring a bell for someone. And I think there is something here. As I say, the literature is converging. It's really there once you start looking at it through the lens of this crazy system of relating quantum gravity and classical in this kind of way. And the signal analysis, if you think about the experiments, CERN has thousands and thousands of signals, and they are, at terahertz rates. These are just burbling along. And the analysis of whether an event has happened or not is performed in hardware and software in enormously sophisticated ways, which isn't described by quantum mechanics at all. It's described by some electrical engineer somewhere who designed a whole pile of electronics without any reference to quantum mechanics at all. So really, there should be a quantum mechanical description of that. Yeah, you want to code all that software? These Turing machines should be coded into quantum mechanics if quantum mechanics is so good. And actually, I suspect it is. But so if it's a really effective signal analysis formalism, it should be able to, we should be able to encode in that kind of non-procedural way. Because we write programs in Fortran or in C or in Python or whatever it may be. But all of that is a procedural way of specifying what the signal analysis will be. And a Hilbert space approach to that, quantum mechanics, would be a non-procedural specification of what the analysis is. And I think the whole thing needs that kind of, we really ought to be doing that kind of analysis as well as just trying to describe the violation of the Bell inequalities with a four-dimensional Hilbert space. Not so much.
Yeah, this maybe if I can add another question there. So
Whoa.
so you this was like on page or slide 23, I think. You you said in the end that that you can always interpret what was it? You can.
This is a one photon state.
Mm-hmm.
This is what a one photon state looks like if you measure it using a field operator. Of course, when we do quantum optics, we never use a field operator. We use projection operators. And those projection operators are non-local because they are state transition. They're effectively, we're just using state transitions. That's why on this slide, I emphasize, this is how we do quantum optics. We're looking at quantum field states, which is what we're working with because it's quantum optics, it's the quantized electromagnetic field without any interactions, essentially. But we're looking at it through these measurements. And these measurements are non-local. This is fine. It works. But if we want to talk about why it's working, we have to start drilling. We have to start drilling into the signals at the gigahertz rates instead of at the event rates of megahertz rates. We have to drill, and that means big data, and it means autocorrelations. It means a whole pile of mathematics that we don't really want to do. But go on.
Does this mean so in a traditional quantum optics approach, I would define the mode on which these states live. So I already restrict myself to a vacuum state which corresponds to a certain frequency, maybe polarization, whatnot.
Right.
So this is what I was aiming at. So usually, in order to make our lives easier and to actually being able to calculate something,
yeah,
or maybe being able to interpret experimental data, we usually make this assumption that we are only looking at the electromagnetic field at a certain frequency, for example.
Absolutely, and you should continue doing so because, heck, the complexities of dealing with all this stuff are horrendous. If you want to know about details, you got to do details. But if you just want to do some quantum computation, it may well be that the best mathematics to use is just a four-dimensional Hilbert space. But underneath it, there's this whole classical system of quantum non-demolition measurements you could be making, you could be performing. After all, if we can perform this non-local measurement, presumably we can also perform the non-local measurement that is essentially the quantum non-demolition measurements are non-local. When you look at it in detail, they are non-local. But if you can perform this non-local measurement, then you can also perform the quantum non-demolition measurements. Of course, if you can't do either, then you're going to have to approximate both by doing what you do. Yeah, so maybe if I go back to this slide, because this way of saying what the state is actually to apply the G modulated, so call G a pure frequency. So if G is just a pure sine wave, then that would be your restriction to a single frequency. So this is effectively just the same as writing zero. Instead of writing these brackets as brackets, you just write bracket zero bracket. And you just put a ket and a bra on the two sides. Yeah. So I'm sorry that this notation is different, but it also, I think it's important as well that one should be able to translate between a system in which one is thinking in terms of vectors in Hilbert spaces and a system in which one is thinking about states. Because a vector is not a state. In the mathematics literature, it really is the case that a vector is not the same as a state. And it's perfectly okay to call it a vector when you're talking with electronic engineers and such like, because yes, it's a state, it's a pure state, it's a way of representing a pure state. But I mean, as soon as you start doing real hardware and such like, you're immediately working with mixed states in any case. It's really, this is just as good a formalism for that. This is just to write, instead of writing this, we could write trace rho hat and then this operator.
Yes, yes.
Yeah. So that's all that this notation does. It just says a state is in a sense a slightly different object from a measurement operator, but it's also mathematically, there's a duality there, of course. But not a perfect duality. Yeah, it's subtle, the way in which it's not a perfect duality. Because not all states can be represented as the trace of a density operator, particularly for quantum field theory. Why not? Do you know? I'm not sure that I can tell you why not, but it's the case in the mathematics literature. You find that some states in quantum field theories, where it's an infinite dimensional system, some states cannot be represented as a trace of a density operator. So they call the states that can be are called normal states. So you're working with in a regime that is kind of outside what we usually work with in quantum optics. It's certainly different. Quantum optics, you can always assume that there's a density operator.
Are there maybe any questions from the audience?
You're welcome to peel away. So if anyone thinks of something they want to ask in the next few days or whatever, then by all means get in touch. You can find my email in those papers and such like. Hopefully in a few days I'll post this to YouTube. I have a YouTube channel, and the most recent one of these that I posted, 30 people went and watched it. So we may possibly see 10 people go and watch this, and you can be one of those. Or you may not want to do that again. Right. Thank you very much, Martin.
No, it's really a pleasure that you went through all the effort in explaining us your work in such detail, and I really appreciate it. And maybe we two can still discuss a bit. I would still have some questions.
Very happy. Very happy.
But yeah, thank you very much, Peter, for giving this great presentation.
Thank you. Thank you.